Hi everyone. In today's lecture, we are going to start the fourth unit. So in this unit, we are going to study the variable control schemes apart from conventional controllers like proportional, integral, and the composite controllers PI, PD, and PID. Apart from that, we have advanced control strategies. So those strategies we are going to see here. So you know that for any feedback control system, one it is one input and one output, which means one measurement and one manipulated variable. So just guess if you want to have or if you want to implement more than one measurement and more than one manipulated variable means then so the answer is multi-loop system. So this one we are going to discuss in this. Okay. So in that the first one is cascade control. First, let me tell you what is cascade control. Then after that we'll decide whether it has more than one measurement or more than one manipulated variable. Okay. For that we'll take a simple system. So this is the CSTR we used to call, that is continuous stirred tank reactor. So the feed is A, then the product is B. So here is the reaction happens, and then it gives, it's an exothermic reaction. Then the extra heat is reduced by the coolant. So this is the coolant supply. In order to maintain the temperature, we use this coolant supply as the manipulated variable. Okay. So in this case, one manipulated variable and one measurement. Okay. So here, as usual, like the temperature of the CSTR is measured by the temperature transmitter, which is always thermocouple in the industry. And since the controller has to give 4 to 20 milliamps output, the temperature transmitter means it also gives 4 to 20 milliamps as output of the process variable. So that is how it is designed. Okay, so the current temperature of this CSTR is measured by the temperature transmitter, which gives 4 to 20 milliamps in that range. And then we have a set point. The set point is also in 4 to 20 milliamps, but which is calibrated to a particular temperature. So both are compared, and then that error signal is worked upon by the various control algorithms, and then that is given. Then that is we have signal conversion, and then this is actuator, this is a control valve. So based on that, we can control the flow rate of the coolant. So this is the simple feedback system. Okay. So here the manipulator variable is this. We all know that since it is a temperature process, the process itself is a sluggish process. It takes time to change. Suddenly we cannot increase the temperature. Suddenly we cannot decrease the temperature. So this is the nature of the process. Okay. So the moment it senses the temperature, and then based on the error comparison or based on the set point and the current value, then based on that control output, if you change the coolant, it may not immediately bring the temperature of the CSTR to our desired level. It takes that time. So instead, in order to give, before you give a control output, let's check the current status of the coolant. So what is the current temperature? And then that current temperature is compared with this controller temperature. Then if you take a decision, then that will be so fast compared to this. So that is how your cascade control works. Okay. So this is the normal loop, but what we do is, since it is a sluggish process, it takes time to understand this, and immediately the temperature won't change. In order to make it faster, what we do is measure we just measure the status of the coolant. What is the current temperature of the coolant? That is temperature transmitter. And then the here based on, this is our primary value. This is also primary variable. So this is the master. We used to say this is a master controller. So the master controller will compare the current value with the set point, and it gives a controlled value so that temperature will be maintained. So that set point or that control output is acting like a set point for the another controller, which is slave. So we used to say slave or secondary controller, because this controller will take care of only this loop and make it ready for the primary controller. Okay. So you know how the manager straight away, manager or anyone or whoever takes care of any particular institution or home. So before you get into that work, you always allow the other people to do small works to make it ready. then only you can easily monitor. Similarly here, we make one control loop, so that control loop control the coolant, or it will sense the current status of the coolant, so that you can easily reach the required value in the or desired point in the CSTR. For that, we have introduced one more loop. So in this case, we have two measurement. So the two measurements are this CSTR temperature and coolant temperature. Since this is the primary variable, so we can say this is the primary variable. This coolant temperature is a secondary variable. So before this effect, or before this controller output impacts this, or before the controller output changes the temperature, we sense the current temperature of the coolant, then we take action. Then if you do this, automatically that sluggishness will be taken care of. Okay, so this is how it works. So it belongs to two measurement type. So cascade controller means it has two measurement. So what are the two measurement? Primary variable and the secondary variable. Since we have two measurements, so we have two control loops. So this, the primary controller is called as master, and then the slave, the secondary control is called as slave. Okay, so for the slave, the master output is a set point, and then it compares, then it gives that value to this, then automatically this target will be reached very faster. So this is how your cascade controller works. Okay, so these are the loops, these are the control components which are commonly used in chemical industries. This is heat exchanger, this is a distillation column, and then this is also distillation column. In this column, we are controlling the top product. In this column, we are controlling the bottom section. And then this is one, this is boiler kind of circuit, boiler circuit, okay? The steam boiler. So first let us take this one. So this is a heat exchanger. Heat exchanger is, so here you, if you have hot liquid means, then this should be colder liquid, so that you have a the transfer of temperature, we can maintain the temperature. So here you have one liquid stream, here also one liquid stream. Okay, so for this liquid stream, this is the inlet and this is the outlet. For this liquid stream, this is the inlet and outlet. Okay, so here I need to maintain the temperature, so this inlet temperature. Okay, or here yeah, I have to maintain this temperature. So for that, first I have to measure this, and that is compared with the temperature controller, and it decides the output that becomes the set point. So before you control it, so first you measure the current flow rate and make it ready for the master controller. So the current flow rate of this stream, because this is the manipulative variable. Okay, so before it acts on this manipulative variable, the other one, that is the another parameter which has closely associated with this is the flow flow rate of this stream one. So measure the flow rate, and this is the set point, and this is the procedure. Take control action. Then if you give this, automatically you can reach this desired point. So this is how it works. The cascade control works. So here two measurements, and then this is the primary variable, this is the secondary variable, and he is the master and he is the slave. So primary controller and the secondary controller. Okay, the next one is distillation column. In distillation column, you have this perforated plates, the plates like this, perforated plates. So how it works is, so here you have to give a feed, and then the vapor goes up, and then liquid comes down. So this is liquid, this is vapor. So we can collect the vapor and condense it. When you condense it, it becomes liquid, and then that liquid is once again feed here. Okay, so likewise this processes keep on continuing. That is, this is vapor. So this is vapor, this is vapor, and then this is liquid. So this liquid is once again, it is fed into this, so that this process continues. Okay, so here if you want, you can apply a different controller. So for example, in this, how it works is, so the main thing is this, at this particular point, I want to measure the temperature. I have to maintain the temperature. So this is your primary measurement. This is the primary controller. Then that gives the control output, that becomes the set point. So before you control this, first you have to measure the current flow rate of this. Okay, because this flow rate will affect this temperature greatly. So first rectify this. Then if you rectify this, automatically you can measure the temperature. For that, you measure the flow rate and then compare with this, then it takes an action. So this control output will have an impact of this set point also. So if you follow this, then your target is easily achieved. Similarly here, the bottom product. So here we have vapor, here you have liquid. So once again, boil the liquid, is converted into steam. So that's why we have a reboiler. So here this is liquid and it's also liquid. After reboil it becomes vapor. Then once again you feed it. So likewise this process continues. Okay. So here in this case, I want to measure the temperature. So measure the temperature and take a control action. This becomes the set point. So before it affects, what you do is first, in order to have this temperature, we need to control the reboiler input. So this is the manipulator variable. So have an eye on that. So what we do is, before we take an action, first we measure the flow rate of the steam. So this flow rate, and then it gives a control variable, I mean the process variable to be controlled, and this becomes a set point. So it compares and it gives the output. Accordingly, the boiler, I mean the steam given to the boiler will be increased or decreased. Automatically this will affect the temperature. Okay, so this is one more second cascade control. So primary controller, master controller, secondary controller, slave controller, we have two measurements. So this is cascade controller. Okay, similarly here I need to, this is a heat exchanger, and then here you have some liquid stream, then this is the process stream. So I need to maintain the temperature. So how do I maintain the temperature? So this process stream will go into inside this pipe. So that pipe temperature is measured and then it generates a control output. So that becomes a set point. Okay. So uh, in order to achieve this temperature, I need to adjust this flow rate. Okay. So to attain this temperature, I need to monitor two important measurements. One is the temperature and the flow rate. So measure the flow rate. Here is the fuel, which is used for combustion, and then that will heat the temperature of this process stream. Okay, so you measure this temperature and you measure this flow rate as well, then decide the controller output, that becomes a set point. This is your process variable, and then this gives error, then that is the control output. That control output is given to the control valve. So in order to achieve this temperature, this the fuel flow rate is very, very important. So measure the flow rate, and you consider both temperature status and also flow status, and give the control action. So in this, master controller, slave controller, sorry, this is master controller, then this is slave controller, and these are the two variables. So these are the few examples for implementation of cascade control in the industrial processes. Okay, so here this is a simple feedback system. Okay, so this also a simple feedback system. So you have process 1 and process 2. For example, if you take this steam boiler, in that, so this is the tank. So here we have a process stream, and then this is so here you have a fuel. So this is one stream, this is one process, and then this is one process. Okay, so the temperature you're going to maintain, this one, this is the main process, so that is a process 1. And then in order to control this process, we are going to take this control process 2. So that is your fuel system is the secondary process. So we take the process and we have only common controller. This is normally a feedback. But if you want to apply uh, secondary controller, means then what you do is take a process 2, which means this, and measure the flow rate. So here, fuel. So take one system. This is the process stream. Okay. So this is the fuel. This is the fuel. This is the process stream. So here, what you do is, so take a measurement of this. So this is flow transmitter. This is given to a controller, flow controller. For this, take temperature measurement, that is given to a temperature controller. This is the set point. So uh, this is the set point, is the process variable. Then the control output is given to the controller. So this is how it works. So here process 1 is, this is process 1. This is P1 process 1, and then process 2 is this one, fuel. So this is process 2. So first we finish the inner loop. So the process 2 is measured by a flow transmitter, and then that is given to a controller. So here For this, who gives the controller set point? From the primary controller, this is a primary controller. So this is the primary controller. So that gives a set point, and then this gives a process variable. Then the error is given to the controller. Then once it is controlled, then it will affect the process. Okay, so this is process one. Okay, and then for the process, we use the measuring device. So this is your TT, this is your FT, and then this is your FC, this is your temperature controller. Okay, and then if you want to convert this to a transfer function, so simple. So here this is GC controller, but secondary controller, this is process 2. So multiply this. So that's why GC2, GP2, and we know that based on block reduction, GC2 GP2 divided by 1 plus GC2 GP2, and then you have to multiply this and this. So which is GC1 and GP1. So this is the primary transfer function, this is the secondary transfer function. When you combine this, then you will have a complete transfer function, or this is a characteristic equation of the cascade controller. Okay, and then here in the cascade controller, there are two important inferences. Since there are two controllers introduced in that, so the two controllers is always basic conventional controllers. So that's the number one reference or inference or takeaway point. So whether it is a primary or a secondary controller, but inside the controller is based on conventional only, which is primary or PI or proportional or PID. Okay, but there is a rule like first concentrate on the secondary loop. Okay, so we always know that proportional is always simple and faster, so it responds so quickly. So choose proportional controller for the secondary loop, so that if it introduces any offset, that offset is taken care of by primary controller. So always for secondary loop, use P controller so that it is faster. So even if you find any problem or any offset in the secondary controller, then that is taken care of by the primary controller. So this is how the rule is. So these are the takeaway points. So always the dynamics of the secondary loop must be faster so that primary can achieve its target. So that's all about cascade controller. So cascade is a multi-loop. In this, instead of one measurement, we have two measurements to achieve the controller within a short period of time. Okay, so the second loop is the second multi-loop control is split range control. Okay, by seeing this picture, you will understand. So this is the reactor. In this reactor, I'm going to use this valve to pass the reactant. So here we have to maintain the temperature, pressure. Then based on that, it produces the output. So this is the reactants, this is the product. You can see two control valves, but only one measurement. So in this control loop, we have one measurement and then two manipulated variables. So we'll see how it works. Okay. So for that, this is one example. First, when the controller output is 3 psi, when the controller output is 3 psi, so how do we take the control output? So first you have to measure the pressure. PT is pressure transmitter. The output is 4 to 20 million. So this is your process variable. And then for the controller, we have the set point. So it compares and it generates the control output. So if it is 3 milliamps, which means you have to open this and fill the reactor, because the temperature, the pressure it shows is only less 3. Okay, which means the pressure is too low. Okay, because 3 is the minimum, 3 to 15 psi, 3 is the minimum. So the current pressure is 3 means you have to allow more. So how do you do that? Allow more reactant. So for that, your V1 should be closed. If V2 is closed, if it is opened, whatever you pass, then that will be driven out. So that should not happen, because I need to maintain some pressure in this. So when the control output is 3, or when it says that the current pressure is 3, then what you do is you have to open this. So that is why when it is 3 psi, you have to open the valve 1. Okay, that time your valve 2 should be closed, because if you open this, automatically whatever it enters, it is given out. So you cannot have your this target pressure. Okay, so for that, when the pressure is 3, then valve 1 should be closed, and valve 1 should be opened, valve 2 should be closed. Okay, after that, you keep on increasing. So when it reaches 9, okay, so it is in between. So in that case, you can slowly open this. So when it is 9, the both conditions are opened only. Then when it reaches 15, then which means this is the maximum. So don't allow any more reactants to enter. So in that case, it is closed. So when it is 15, V1 is closed. And then if you maintain that, then it may burst. For that, you have to release it. So this is how it works. So you have a coordination. So this is the valve coordination. So we have to decide that. The same thing is expressed in this. So this is the controller output signal. This is the valve stem position. So this is valve 1. So when it is 3 psi, your valve 1 is opened and then valve 2 is closed. Okay. When it reaches 9 psi, then both are opened. So here open means it you see the stem position, and then this is also open. Then when it is 15, then your V1 is completely closed and V2 is open. So this is how your split range works. One more example is, this is the steam header. See here I have to measure you have to maintain the particular pressure. So that pressure is measured over here. So this is your process, a current value of process variable. And then here you have the set point. So this is plus, this is minus. So it generates error. Then that is given to the algorithm. Then that algorithm produces some control output. Then that output is splitted. So you can see how many is, so that particular output is given to various boilers. Okay. So how it is given, a portion is given to the control valve, then the control valve will control the flow rate. Okay. So this is how it works. So one measurement, but you have more than one manipulated variables. Okay, so that's all for today. So we have learned cascade controller and split range controller. Even in split range controller, we have the normal conventional controller only, P, PI, PD, PID. Okay, because this is a pressure process, we are okay with pressure controller. Even there is an offset, we can increase again to reduce the offset. Okay, so this is how your split range works. Thanks for watching.